So time again for another video presentation for you here. And today what we're going to talk about is graphing basics. Something that you are familiar with from your math classes, and now we're going to apply it to physics. So these are the basics and how they're going to apply to our class. First off, I'm going to consider a car driving at an average speed of 30 miles per hour for 2.5 hours. Something that we've talked about already in class, something similar to what we've talked about. So we are going to represent the information symbolically. That's our goal here. And really we've already been doing that, representing things symbolically. Our equations are a symbolic representation of the motion. Here we're going to do it with a graph. And to start off with, we are going to have a chart. So the chart is going to indicate the information that we'll later graph. So like all of our stuff here, we want it to be clear, and clear means the units are going to have to be in there. The number 30 doesn't mean too much, but the number 30 with a unit to it does mean something. So what we're going to do is, first of all, identify what the chart is about, and I'm giving it a title here, the distance for the car, averaging 30 miles per hour. Now 30 means something. Okay, so what I've done here is I have a column for the time, and the time is in hours, as you can see, and I've chosen to go up in half-hour increments. And I'm going to also put the distance here in miles. Maybe you want to pause now and see if you can complete the chart successfully. And we're back. So, how did you do? This is what I came up with. For 1 hour, the car was going 30 miles. So in a half hour, it would go 15 miles, and so on. So your chart and my chart should look identical at this point. All right, now we're going to start building the graphs. So as I build up the graph piece by piece, please do it with the graph that's on your note outline as well, so that you're going to have a complete graph by the end of it. We'll build it together. All right, so before we start building the graph, what else might you want to know besides the distance and the time if you were going on a car trip? What other questions would you have? Well, maybe you'd want to know, what kind of car is it? I always picture at this time my first car, the '73 Ford Gran Torino. Ah, that was quite a car. I miss that car. So whatever car you want to picture is all right. Maybe you want to picture who's in the car with you. Maybe you wonder where you are when you're driving. That's always a good thing. Where am I? GPS's help with that these days, right? And maybe you want to know where you're going. Well, none of these things are going to be on the graph, but they're certainly important to the trip, right? But we're just going to be talking about the kinematic information, the description of the motion of the car. Okay, so the first thing you're going to need on your graph, and you can start adding it in as well, is a valid scale for the vertical, that's the up and down, and for the horizontal, that's the side-by-side horizontal axis. And a valid scale means that the numbers on your scale are going to go up in equal increments. So here I've chosen a scale where each one of these larger lines here is 10. So if this one's 10, the next one's got to be 20, and so on. On the horizontal axis, I've chose 0.5 for each one of the big lines. So 0.5. Then 1, 1.5, equal increments. That's what a scale is, equal increments. Okay, so you can go ahead and add a scale to your graph, and maybe pause, and then come back to the video. And we're back. All right, here, just to show you, I've changed my scale. I've changed my scale to be 20 each time. It doesn't matter what your scale is, as long as all the points can be put on the graph, and that there are equal increments. Here I've stuck with a half an hour on the x-axis, the horizontal axis. I'll change that later. All right, the labels are important. The numbers themselves, even with a valid scale, don't mean too much, so you're going to need to indicate what you're graphing, in this case distance, and the unit for it, in this case miles. So that's what I'm going to be looking for there. Labels, so we know what we're looking at. On the horizontal axis, or what they sometimes call the x-axis, I'm going to put the time in hours. Okay. All right, so there are at least two variables that are put on a graph. And we've already mentioned them, but what are they? Do you know what they are? Well, of course, They are the distance and the time, and that should make some sense. It's the distance and the time that we're graphing here. Okay, so the graph also needs a title. All of our graphs will have a title to them, and the custom is to give it a title of the vertical variable versus the horizontal variable. Can you think of what the title is for our graph? Well, we're always going to go along with this idea of the vertical versus horizontal, so it's good to get into the practice of thinking about it. But for our case here, it would be the distance versus the time. So distance versus the time is necessary for the title. Now I've added in for a 1973 Ford Gran Torino averaging 30 miles per hour, but distance versus time will be enough. I just threw this in here so I can go down memory lane with my first car ever. Ooh, that was a nice car. All right. Now, you can see here again, I've got my valid scale, I've got my labels, I've got my title, I am good to go. Any ideas what the next step is? Well, the next step is we're going to add the data points. So we're going to plot the points from the graph. Maybe you want to pause and give that a try, or maybe you want to see what I did. At any rate, I came up with these points. And here, if you notice, I've once again changed the scale. This time I've changed the scale on the horizontal axis. So a half an hour was 15 miles, and 1 hour was 30 miles. So I've plotted all the points, and that's what I'll be asking you to do as well, to plot all the points from the graph. Okay, another thing that every one of your graphs are going to need to have is a trend line. So we're going to put a trend line in here. Here, the trend line is pretty obvious. All the points were right along a straight line, so you can connect the dots here. But connect the dots is not always the way to make a trend line. Here it's convenient because they're all right on that line. So that makes connecting the dots okay for this example. I'll give you an example in a minute where that's not going to be okay. Okay, now we'll talk about the slope of the line. Now the slope of the line is talking about how fast the vertical variable changes with respect to the horizontal variable. In this example, we're talking about distance and time. How does the distance change with respect to the time? So in your math classes, they probably talked about this as rise over run. The rise being the vertical and the run being the horizontal. So the change in the vertical over the change in the horizontal. Okay, and that's going to be a good way of calculating the slope. So the slope, you can use any two lines as points on the line as long as the second point is after the first point. So any 2 points should do it for your line. Any point along the line should give you the same slope. So we're going to use the first 2 data points to talk about the slope of our line. So the first 2 data points are, well, the first one is 0, 0. And I always like using 0, 0 when I can. It makes the math come out easy. Our second data point is 0.5 and 15. Do you see that on your chart and on your graph? You can check back for that. But those are our first 2 data points, and we're going to use that to find the rise over the run. Now, this triangle is a symbol, a math symbol for talking about a change. And that's what you're really looking at, the change in the vertical over the change in the horizontal. So we can talk about that as being the change in the vertical over the change in the horizontal. I see it's cut off there a little, but it should say the change in the vertical over the change in the horizontal. Well, a change in anything is where you ended up minus where you started. So what we're going to do is we're going to be talking about the change in the y in a general case. In this case it's distance, and it'll be the second vertical variable minus the first, and in the x direction we're going to be talking about the second horizontal variable minus the first one. Alright, so in our case here it's going to be the change in the distance over the change in time. And now, in looking at my points here, I'm going to take my 15 minus 0 and then divide that by 0.5 minus 0. So that's going to give me 15 divided by 0.5, or 30 miles per hour. And the units are important. 30 miles per hour is different, as I say, than 30 inches per second or some other increment or unit. Okay, so you can do this using any 2 points on the graph. So go ahead and pause, use any 2 points, and convince yourself that it still comes out to 30 miles per hour. Hey, how did it go? Welcome back. Maybe it gave you troubles. This can be a confusing topic. Graphing can be. So please use this as a chance to find out what your questions are so you can ask them in class when we get together again. Okay, so how are the units important? Well, I've said it a bunch of times, right? 30 is just a number. 30 miles per hour indicates something different than 30 inches per second or any other number of units, right? So that's how that's important. And what does the slope of the line represent? What did that 30 miles per hour? What is the change in distance over the change in time? Well, hopefully you got a good idea here for this graph. And all year long, that'll be the challenge. What does the slope represent? It's always something related to our class and related to the topics that we've talked about. In this case, I hope you recognize that it was speed. 30 miles per hour is the speed, and that's the change in the distance over the change in time. The next thing that we want to do is we want to talk about the equation of the line. Now in math class, you may have done it in general terms, and they would have talked about the idea of y is equal to mx plus b. Y being what's represented on the vertical axis, and x being what's represented on the horizontal axis. M is the slope, and b is the y-intercept. Okay, so for our example, the equation would be d is equal to 30t. Now, when you solve these, we're never going to leave it as y and x. They're not a generalized thing like they would be in math class. All of our examples that you'll do on assignments and tests and quizzes, they're going to leave the y and x. We're going to take the y and x and we're going to put what they represent. Here, d, the distance, is represented on the y-axis. The slope is 30 and the x-axis is the time. So y and x won't get you full credit. The y-intercept is 0 because it intercepts the line at 0, 0, and there's our equation. Now, how about this, right? Since 30 is the speed, you could also say it was d is equal to vt, right? Where v is the speed. So I just want to show you that and ask you, d is equal to vt. Does that look familiar to you? Well, I hope it does because d is equal to vt is one of our equations. And the equations for your line are always going to go back to one of the equations that we've been dealing with. D is equal to vt in this case. Okay, so what do we get out of this graph? Well, we get the speed. By finding the slope, we know the speed. We also have an equation that means we can figure out what the distance is for any time. Not just the points that were on the graph, but for any time at all. Okay. Now, just to point out, trend line is a generalized term. It applies to curves also. And in this graph, the trend line would be like a curve, I guess, right? So it would look something like this. But trend line is used to talk about curves as well as the straight line. Okay. This time around, all of the points were right on a nice straight line. So connecting the dots worked out perfectly. But if this isn't the case, like in an experiment, you can't be exact all the time on an experiment, and sometimes I'll give you data that jumps around a little as well. So for these, you would use a best fit trend line. So we won't simply connect the dots and get some kind of shape here. We'll draw a line that kind of looks like where most of the data points go. And to me, this would look something like this. So here's a challenge. Go and find the slope and the equation of this trend line. Why don't you pause and give that a shot? And we're back. How did you do? Well, this is what I got. I got a slope of 3, and I got an equation of y is equal to 3x. But I got another question for you. How did you do? If you had trouble with that, please bring your questions into class and we can go over it, right? And yet, I got another question for you. Why is this graph particularly useless for finding kinematic equations? Well, the answer is this y and this x. Remember, I told you, we're not going to be dealing with the generalized y and x. What do they represent? They're just y's and x's. They're just a slope of 3. Now, if you added in distance and time, now we got something useful for physics class. All right, that's it for today. Please do bring your questions to class, and I look forward to seeing you there.